It's open strings. That's interesting enough. And there's a lot of things we have to get straight here. And many of them will carry to the closed string. And but really, with this open string, we're going to encounter finally the real things, the stuff that eventually made string theory into a candidate for a unified theory. The fact that you're going to get gauge fields out of string theory, for example. Where do the gauge fields come from? That's what we're going to answer. We're also going to see the critical dimension appearing. We're going to see finally the Virasoro operators in all of their glory and things like that. So there's lots of things. And we begin by just reminding you of a few relations that we've derived over the last few days. As you notice, there's quite a bit of notation. So we'll just try to put it all together now. So quantum open strings. But first, we begin with what were our classical results. Well, we took a light-cone gauge in which x plus was equal to 2 alpha prime p plus tau for open strings. The light-cone gauge condition had other things. That had a uniform energy density along the string defined for in the light cone, as opposed to just the conventional energy density, the sort of energy density associated with the direction that you chose. And our momentum densities and our the other component of the momentum density associated to boundary conditions are given by 1 over 2 pi alpha prime x mu dot and minus 1 over 2 pi alpha prime x mu prime. Another thing that we discussed was that there were these transverse Virasoro operators, and one in particular was 2 alpha prime p plus p minus was equal to L0 perp. Now, continuing with these things, we also have that p minus for the open string. It's related to this, but we want yet another expression. Is the integral from 0 to pi over the string of the momentum density p tau minus. But p tau minus is nothing else than this 1 over 2 pi alpha prime x dot minus. So the sigma 1 over 2 pi alpha prime x minus dot. Now we had, remember in the light cone, we solved for x minus, and we in fact solved for x dot minus plus minus x prime minus. And from there, we got all our Virasoro operators. So x dot minus is something we solved for, even though I didn't quite write those formulas. They were of the form, if you want to remember, something like x dot minus plus minus x minus prime was some numbers times xi plus minus dot xi prime squared. So to get x minus dot, you were adding these two equations. You put one below the other and you add them. And so the answer here, 0 to pi d sigma, 1 over 2 pi alpha prime. And when you do that with all the constants there, which you have that precise formula in your notes, 2p plus, you can see that you get this thing, xi squared plus x prime squared. When you square and add, these squares remain, the cross term. cancels out. So we have all this. Now, this is related to energy, as we'll see very soon, and therefore I'm going to try to write it in Hamiltonian way. So remember, when you try to write an energy or a Hamiltonian, it should be expressed in terms of coordinates and velocities or momenta. And our momenta are these ones, this p tau, because their integrals are the momenta of the string. So I'd rather change these ones to p's. So this becomes 0 to pi d sigma 1 over 2 pi alpha prime, 1 over 2 alpha prime, 1 over 2 p plus. And here I get each x dot is 2 pi alpha prime. So I get a factor of 2 pi alpha prime squared. And I get here p tau I, p tau I. Now I factor out the 2 pi alpha prime squared, so I get here 1 x prime I over 2 pi alpha prime squared. So now we just cancel 1 2 pi alpha prime, 1 2 alpha prime, 1 over 2 plus. So what do we get from here? A nice result. Pi over 2p plus integral from 0 to pi d sigma p tau I plus xi prime over 2 pi alpha prime squared. Okay, that's basically the kind of formulas we're going to need in the next few minutes as we set up the quantum string. But, you know, things at this moment, they're a little messy. This whole thing, it will simplify. It will become neater. You know, you can't expect to remember something like this square by heart, but it's sort of interesting. It's a p squared plus an x squared. That sounds very harmonic oscillator-like. And indeed, the whole string is an infinite collection of harmonic oscillators, as we will see. So let me remind you what we had for the particle. For the particle, we had Schrödinger operators that were xi, x0 minus, pi, and p plus. So we're now supposed to invent, one more thing, if you wish. Here, the equation of motion of the string is x mu double dot minus x mu double prime equals 0. Equation of motion. Now, we're going to try to invent again, just like we invented the Hamiltonian for the particle, invent the Hamiltonian for the string, but we need to decide what are going to be the operators. This is, in a sense, the most important decision you make. Who are your quantum operators? And the analogy is so good that we're going to be able to just see from here. So for the string, the Schrödinger operators are going to be what? Well, xi, that sounds good, but xi now should be a function of sigma along the string. Now you would say, how about tau and sigma? Not yet. These are Schrödinger operators, time-independent operators. So for the particle, you think of xi as a dynamical variable because at any given instant of time, well, the value of xi is all you need. But you need here the value of xi all over the string. So xi of sigma is the right variable. All our x's are x's of tau and sigma. So tau should be remembered that it should come through the Heisenberg equations of motion. X0 minus, you leave it like that. It's a zero mode. No way we're going to put a sigma in here. Now, pi, that probably needs to be changed as well, because yes, there's a momentum of the whole string, but each little piece of string, like being a little particle, has a momentum. There's the momentum density, so their integrals are the momenta. So we'll do that. We'll put p tau I of sigma as next dynamical variable. And finally, we'll put p plus here. That's still a number. It used to be a number in the classical theory. And we have there a reasonable set based on what we've learned before. At this moment, of course, we could go Heisenberg. If you go Heisenberg, you would write xi of tau and sigma, x0 minus of tau, p tau I of tau and sigma, and p plus of tau, with the expectation that once you invent the Hamiltonian, you discover that this p plus and x0 minus are constants of the motion in the Heisenberg picture, constant operators. And in that case, that would be intuitive. This would be what we want. Of course, is the issue of inventing the Hamiltonian, but even before inventing the Hamiltonian, we have to write, and that's still the part of your work, the invention of the commutation relations. What should be the commutation relations? Well, here we go. Xi of sigma with p tau I. This is coordinate and momenta. That must be related. And we'll put it at a different sigma prime. What should this be? Well, we sort of know that this is x and coordinate and momenta, so this should be an I, eta, or delta, doesn't matter, ij. And these are at different points of the string. Things that are at different points of the string, we would hope they commute, because this is an instantaneous string, so a measurement here, a measurement there at the same time, they should commute. So your intuition, maybe from quantum field theory, would tell you that what you expect here is a delta function of sigma minus sigma prime. Now, there's no, I'm offering at this moment no derivation of these things. At some point, you really cannot derive them. What is quantum field theory? Is taking a Lagrangian and postulating some commutation relation between the fields and the momenta, and then constructing something that makes sense. Here we're postulating this transformation, and we hope to get something out of it. Now, the other thing that I must do, of course, x0 minus with p plus is equal to minus I as before. And all others are 0. All others 0 is a very important statement, of course. 0. Now, if you were now in the Heisenberg picture, remember the Heisenberg operators are obtained by unitary action on Schrödinger operator. A Heisenberg operator is a unitary operator that generates time evolution in your system times the Schrödinger equation times the Schrödinger operator times U. I think it's U dagger here in the nice notation. So commutation relations that hold for the Schrödinger operators hold for equal times in the Heisenberg picture. So we will have xi of tau and sigma. That's why they're called equal time commutation relations, because they originate from commutation relations of Schrödinger operators, tau sigma prime is equal to I, eta, the same thing, Lij delta of sigma minus sigma prime. These are nice equations. Okay, now what? The Hamiltonian. A guess for the Hamiltonian is what we're going to try to do. And we do it again like the particle. So, you know, the idea of having done all this particle in detail, and even though I'm pretty sure it has been intense. There's a lot of formulas, the Lightcon operators, all these things, but we're going to see them again and again, and they're happening again and again. And, that's okay. So we think of this. We want in the Heisenberg picture dd tau to be the time evolution. So dd tau is dx plus d tau times ddx plus. And remember, ddx plus is the thing whose evolution is created by p minus. So dx plus d tau, here we get 2 alpha prime p plus ddx plus. So dd tau, what we want to know is essentially just this times a number, and this thing over here, this time evolution is created by its conjugate, which is p minus. So our guess for the Hamiltonian is therefore 2 alpha prime p plus p minus. Now, 2 alpha prime p plus p minus, if you see up there, is actually something quite nice in this theory. So it's equal to L0 perp. Now, in the classical theory, all these things are numbers, and p plus, p minus are numbers, and these operators are numbers, and they're all time independent. If you remember our classical solution, maybe I can remind you of a formula there. Yes, we found the LMs were this sum p and z, alpha I n minus p, alpha pi, and these were numbers, and that's sensible. Your Hamiltonian is time independent in any reasonable way. Now, what we're going to do is using a Heisenberg Hamiltonian, but that's not going to change the picture. Think of this for a second like that, but then immediately let's put just the p minus here. So one thing to remember is that the Hamiltonian is just L0 perp. But we're going to get in trouble with L0 perp very soon. It's a very interesting trouble. So I'll put a question mark here because that may quite not be right. There's another thing that happens in this stuff is that you're multiplying operators at the same point. These are at sigma, and sigma, and sigma. And multiplying operators at the same point in quantum field theory is problematic, and we're going to get into those problems now. Happily, it's very tractable and very nicely how you can put them all together. So let me write the Hamiltonian in this way. And I'll put a tau because, in principle, everything has a tau still. So 2 alpha prime p plus p minus, I go here to this formula, and I just write it This would be the integral from 0 to pi d sigma p tau I of times p tau I, all this of tau and sigma, plus xi prime over 2 pi alpha prime squared, and this is still of tau and sigma. So this is our Hamiltonian. Now, we shouldn't worry too much. This Hamiltonian, in the Heisenberg picture, you have the equation of motion that any operator, tau, say, here you can put a sigma if you wish, will be given its time evolution by the commutation with the Hamiltonian. And these are for Heisenberg's from Schrödinger's without explicit time dependence. This is the Heisenberg equation of motion for Heisenberg operators that come from Schrödinger operators that have no time dependence. Now, the Hamiltonian comes from a Schrödinger operator that has no time dependence. It's based on these operators, and you just make them Heisenberg. So it's a perfectly, there's nowhere an explicit time in here in all the operators that we've constructed except in X plus. So the Hamiltonian, you can put for Xi the Hamiltonian and conclude that H tau, so I dd tau of H of tau, would be the commutator of H with H, which would be 0. So the Hamiltonian is a constant in time, but that should not mean that you can erase the times here. This thing is time dependent, this thing is time dependent, but the sum should not be time dependent. That is the same thing for a harmonic oscillator Hamiltonian. If you write it, the x of t squared and the p squared term and the x squared term, each one by itself is not time independent, but the sum is. So let's leave it like that, and let's do just one test with this Hamiltonian. Well, I can do a couple of tests that are sort of quite reasonable. For example, x0 minus, what is its time dependence? Well, you would have to compute, the x0 minus here. What is the time dependence of it? Well, you would have to put it in here and compute the commutator of x0 minus with h. But if you look at your list of non-vanishing commutators, they are here. And x0 minus only fails to commute with p plus, and there's no p plus here. So x0 minus commutes with the Hamiltonian, and therefore x0 minus is really, x0 minus of tau is really x0 minus. And the same thing for p plus of tau. P plus only commutes with fails to commute with x0 minus, and there's no x0 minus anywhere here. So those operators are really p plus of tau is really p plus. And let's do one that is a little more non-trivial. So let's assume we want to compute the time dependence of xi of tau and sigma. Well, then I would have to do the commutator of xi of tau and sigma with the Hamiltonian, which is pi alpha prime integral d sigma prime. I'll put the Hamiltonian with an integral of this sigma prime to distinguish this sigma. And you would have p tau I of tau and sigma, p tau I of sigma prime, of tau and sigma prime, plus xi prime, all of tau and sigma prime over 2 pi alpha prime squared. Close this and close the bracket of the commutator. Commutator is here. Let's raise it so you can see it all better. Okay, looks messy. But x's commute with x primes. The prime derivative is a very innocent derivative. It's a derivative along space on the string. Has nothing to do with the commutators. You can have, for example, we know that x of tau and sigma and x of tau and sigma prime commute. Because we said all others are 0, so an x and an x commutes. Therefore, an x, you can take this equation and take a sigma derivative or a sigma prime derivative. So this is still 0. It's not so, you get into trouble if you try to take tau derivatives, because there's the same tau here, so you're going to get tau derivatives on both sides, and that's going to be an issue. And moreover, the tau derivative of a quantity is really a momentum. So you have to be a little careful with that. But still, this x definitely commutes with x prime. The only thing that doesn't commute is this x with this thing, that at this stage having an I here and a repeated I here is just a bad thing. So this should be a j and a j. Then we have a commutator that is non-vanishing between this and this p and this and that p, but they're in the same footing, so that's a factor of 2. So what do we get? 2 pi alpha prime, and then we have integral d sigma prime. Let me put the commutator here. xi of tau and sigma. Oops. D tau I. I did a little damage to this. The clips went out. I'll put it like that. I don't know if it will work. I think it's good enough. Yeah. So p tau j of tau sigma prime. And then you have another p tau j of tau sigma prime here. I think that's all there is. So this is 2 pi alpha prime integral d sigma prime. And now this thing is I eta ij delta of sigma minus sigma prime. That's the commutator. P tau j of tau sigma prime. So the integral is immediately done, and we get an 2 pi alpha prime times an I. The eta transforms that j into an I, p tau I, and the sigma prime just picks the value of sigma here. Okay, so I xi of tau and sigma is all that. Therefore, xi dot of tau and sigma is equal to 2 pi alpha prime p tau I of tau and sigma. And what did we get? We got one of our classical equations of motion in Hamilton. For the top equation over there on the top blackboard, x dot is 2 pi alpha prime times p. If you wish, you could now calculate p tau I of tau and sigma dot, and it will be related to x prime as well, xi prime. From these equations, you can get the wave equations and basically reproduce all the classical dynamics that you know for the string. No, it will be double prime, I think. Yeah, it will be double prime. So I will not do more checks on this thing. I take it that this Hamiltonian is good. So the only thing pretty much that you need to check at this moment is the other equation for p tau dot. And it's something like that, so that then this equation of motion x double dot minus x double prime is equal to 0 is reproduced, and the Hamiltonian is good enough for us. So now that we have the Hamiltonian, we need to understand more concretely what it is. All these integrals over sigma and tau and equal times are good, but they're not like the kind of things you can grab with your hands and calculate so easily. So what are we going to do? We're going to try to find what this implies for our expansion modes. So we have these commutation relations. And there's a technical result that I don't want to. So calculations here can be a little long, not very long, but 1 page long or things like that. And we don't want to get into too much technicality because we lose the picture. So I'm going to show you the key steps now. And if you're interested, do them at some stage. But the key steps are that we've learned already with our modes that these things like x dot plus minus x prime are the most useful combinations to do any calculation. So you want to rewrite the commutation relations in that language. And if you begin with the commutation relations imply that the following is true. X dot I plus minus x I prime with x dot j plus minus x prime j. I'm sorry, I should have left a little space for tau and sigma here. And x dot j plus minus x prime j of tau and sigma prime. So when you look at this, you should think xi, if you're doing the dot, you should view it as what it is here, 2 pi alpha prime p tau I, if you want to compute the commutator. Because it's a shortcut to write these things. Our commutators were written in terms of p's and x's, but we'll write it like that. So what does this give you? Well, this is useful because you remember these expansions that were pretty nice for these operators. In fact, the expansion, I'll write it here, is that x dot I plus minus xi prime is equal to square root of 2 alpha prime sum over n belonging to z alpha ni e to the minus I n tau plus sigma. These expansions are now the solution of the Heisenberg equations of motion. You see, we're solving classical equations, but the whole thing about the Heisenberg quantization is that the equations of motion are the same as in the classical theory. So the solutions are the same. So in the Heisenberg picture now, we use the notation we use in chapter 9, and this is the solution. This solves the Heisenberg equation of motions of this form. But now we have to be aware that these things that we used to call numbers are operators. These are operators now. And if I want to do the commutation relations, working with x and p, or x dot and x prime and x, it's very complicated if you try to just understand what those commutation relations imply for the alpha oscillators. So that's why we want something like that. And even though we're not going to use it too much, it's important that something like this exists. This is 4 pi alpha prime I eta ij dd sigma of delta of sigma minus sigma prime. Since you're doing things with commuting momenta with x primes, the prime derivatives sort of have survived and now differentiates the delta function. So this formula follows from the formulas above with a little bit of work, and they're very useful because these things are now expressions, nice expressions in terms of the oscillators. You can also show, I'll write it in words here, that if this sign and this sign are opposite, or this minus and there would be a plus here, if the signs are opposite, the result is 0. Now, we have, so I will put it here just schematically, x plus minus x prime, commutator x dot minus plus x prime is 0. So here comes a question that one needs to calculate now. We have these expansions, and these are now operators. So if I substitute here in this formula, what do I get? What do I learn about the commutation relations of these oscillators, or these expansion coefficients? And what we learn is the following. From this equation that we can call equation 2 and equation 1, from 1 and 2, we get the following nice relation. Alpha mi commutator with alpha nj is equal to m delta m plus n, comma 0 delta ij. So this is it. It's a very strange looking commutation relation, actually. There's a label m, a label n, I, and j, m, and this thing here. So look what has happened. If you had a simple harmonic oscillator, you'll have an A and an A dagger. That's it. Here we have lots of them. Well, we'll call them alphas, but soon A's. There's n, a label that is sort of like a mode. And then, moreover, there's a direction, because every spatial direction has its oscillators. Remember, the xi has the alpha I n. So there are infinite number of oscillators for each spatial dimension. It's a lot of oscillators. So we need to understand this a little more. So let me remind you. So at this moment, happily, this part of the computation is sort of a little heavy. And once you have this formula, getting this is not that bad anymore. Most of the books actually don't do it this way. So many of the books don't do it this way. They do something less satisfactorily, in which you sort of guess this and then check that these commutation relations above work. That's an okay thing, but it's nice to be able to derive it, and this is how you derive it. So let me remind you what xi was. We had xi dots plus xi prime, but just let's see what this was. x0I plus square root of 2 alpha prime alpha 0I tau plus I square root of 2 alpha prime sum from n. This was more complicated. 1 over n alpha n I cosine n sigma e to the minus I n tau. All right. This we wrote, and this was the solution of the classical equation of motion. Now it's the solution of the Heisenberg equation of motion. If these are operators, and if this is an operator, and if this is an operator, that solves the Heisenberg equation of motion. Now, this was a real quantity. So in the quantum theory, it should be Hermitian operators. If it is a Hermitian operator, then x0I is Hermitian, alpha 0I is Hermitian. And in order to get this to be Hermitian, remember when you complex conjugate, or when you take the Hermitian conjugate of all this I changes, so n goes to minus n, and you just check it that the condition that this is Hermitian is that alpha I n dagger is equal to alpha minus n I. So the negative alpha n's are the Hermitian conjugates of the positive alpha n's, or vice versa. So we will do a slightly different writing of this oscillator. So we'll take this. We'll take alpha ni. Now the factors of n here are sort of unusual, and the factor of m here is unusual, because whenever you have creation and annihilation operators, you know that a dagger is equal to 1. And that we want to keep. So let's try to see how we get creation and annihilation operators here. So we'll define this to be square root of n times a n I. So look, square root of n a's as opposed to alphas. They're very different. But I will take this to be just true for n greater or equal than 1. Because then I know that alpha minus ni is the dagger of this top line. So it will be square root of n a n I dagger. And this will also be, because I took this equation and I just took its dagger, this is also for n greater or equal than 1. So the main thing that this definition does is to note that the thing that you should notice is that when you work with alphas, the n's belong to z, all integers. When you work with an's, or an daggers, the n's belong to z plus, the positive ones. There is only a1, a2, a3, a4, but there is alpha 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. The negative ones are going to be interpreted as creation operators. We'll see that in a second, because n is always positive in this equation. So this is a negative alpha, is a creation. A positive alpha is a destruction. That's a convention that everybody uses, happily. Everybody uses that. They don't define it the other way. And that's good to know. So our small challenge is to now interpret this commutation relation, which is a very famous. Now, whether you use alphas or a's is your choice. In fact, it's sometimes more convenient to see a's because they're more like harmonic oscillators. But the alphas can make some computations easier. So let's see this. So I will look at this equation. Look at the equation, I don't know, what are we now? 1, 2, and 3. This is going to be equation 3. Look at 3. At 3. And take n, put minus n. That simplifies something. So let's look at it. Alpha mi, alpha minus nj is equal to m delta mn. Now, this is something I didn't say much, but so let me say a little bit. Here, these two operators commute unless the sum of m and n is 0. So only if m is equal to minus n, you get some number on the right-hand side. And if these two things don't add up to 0, m plus n comma 0, you get that they commute. So an alpha 2 commutes with any alpha minus 3, but it doesn't commute with the alpha minus 2. So I put n to minus n, so it's just a rewriting of the formula. I didn't do anything else. So now let's take m and n opposite signs. If m and n have opposite signs, the right-hand side vanishes. So let's take, for example, m positive and n negative. If m is positive, I can use the formula there. This operator is proportional to ami times the number. If n is negative, as we said there, this is a positive number. So this is a n I want to write like that. If n is negative, I should have. No, I'm sorry. I want to show that suppose m and n have opposite signs. I don't know why I'm getting this a little confused. Okay. Okay, I should say it this way. If n is negative, then minus n is equal to some n prime that is positive. So in that case, this is a n prime j, and this must be 0. N is negative minus n is n prime positive, and therefore you get this. If you take m negative and n positive, you do the same thing. If m is negative, this is of this form, so you have here an a m I dagger. But this is with m prime. I'm sorry, I didn't write this very well. So minus m is equal to m prime, which is positive. So I'll put the m here. And if n is positive here, I can just directly say this. So it's a n j dagger as well. But these are 0. So basically, you know, it's a little confusing with the signs, but I think I now got it totally right. This says that the A's commute and the A daggers commute. Now, finally, you want to see what the A and A daggers do. So you take M and N, both positive. And then what do you get? If M is positive, you can use this formula. So it's square root of M. Now we want to get the numbers, because then things are possible. You have A. M is positive, so here you have A, M, I. Now, N is also positive, so you now use the other equation, square root of N, A, N, J, dagger. And this will be equal to M, delta Mn, eta Ij. So what do we get from here? We get AMI, ANJ, dagger is equal to M over square root of Mn, delta Mn, eta Ij. And this, since M is equal to N, this whole thing is 1. The delta function imposes that. So this is just eta delta Mn, eta Ij, which I'll rewrite here because it's a very important equation. AMI with A, N, J, dagger is equal to delta Mn, and you can put, if you want, delta Ij. So these are really harmonic oscillators. Why? There's an infinite number of them, but an A with its corresponding A dagger is equal to 1. And its corresponding must have the same transverse direction and the same oscillator number. So every oscillator has a number for oscillator and has a number for the transverse direction. And therefore, this is an infinite collection of perfectly well-normalized harmonic oscillators. There's two little things here. The zero modes, alpha 0I, you may remember, is 2 alpha prime pi. That's still true. You take it from mode expansion, you do the p tau. This we did in the past, that is still true. And certainly in the quantum theory, x0i and pj give you I delta Ij. So actually now you really have a lot of power to do things with the explicit calculations, because everything has been discretized. You know, most of us prefer to work with discrete things than with continuous things. This sort of integrals of continuous stuff are delicate. And we will see right now, because in this instant, we're going to run into the main problem that is really quite fascinating problem of this theory. Let's see what happens. So, well, we have derived following statements. In the classical theory, we solve for the x minuses, and we also have to solve for the x minuses here. And we got basically that the alpha n minuses were proportional to ln perps. And let's look at the definition of ln perp. This is 1/2 p belonging to integer I n minus p alpha pi. This is what we had before. And you look at them and you say now, well, there's room for trouble here. First, it's an infinite sum, and I actually don't know the order that these two should be put in. In the classical theory, we didn't care. We put it any order we wanted. Now we should care because these are operators and they don't commute. They don't commute. So which order should I take? Well, let's see. Do these commute or don't commute? In order to fail to commute, their indices must add up to 0. So does this add up to 0? P and n minus p adds up to n. Oh, so we're in not so bad shape. For n different from 0, this is okay. And by saying it's okay, we mean that it's well defined. You could have written it in any order. But let's look at L0. L0 is presumably problematic. So let's look what it is. L0 perp is 1/2 the sum for p equals over all integers of alpha minus pi, alpha minus pi. Well, alpha pi, I'm sorry. This is not so clear. Let's go slowly here. This is 1/2 alpha 0i, alpha 0i, plus 1/2 sum p equals 1 to infinity. And now I'm going to break the sum into all the positives and all the negatives. So let's begin with all the positive ones. So it would be alpha minus pi, alpha pi. And now I got all the positive ones. Now let's get all the negative ones. Well, I can still sum over p1 to infinity, but change p to minus p. So I put it here, alpha pi, alpha minus pi. Now, one of these sums is good and one of the others is not very good. Which one is good? Well, whenever you have an operator, it's going to act on the vacuum and things like that, you want it to be well ordered. So when you write the Hamiltonian for the oscillator, you write A dagger A. The destruction operator should be to the right. Now, with p's positives, the positive piece, this is destruction. So this is good. And this is creation destruction, so this is no good. So we're facing a real difficulty with with L0. We actually have an ordering ambiguity. I don't know what the classical theory suggests. Should it be, how should we have written these things? If we write them like that, there is a problem. So let's reorder this. So what do we get? We get, first, this thing with the expression for alpha 0. This is alpha prime, pi. Plus, now let me replace this by the thing in the opposite order plus the commutator. So the thing in the opposite order is going to be identical to that, so this 1/2 will become 1. So we get the sum, p equals 1 to infinity, of alpha minus pi, alpha pi, plus the sum of the commutators. So 1/2 sum from p equals 1 to infinity, the commutator of alpha p with alpha minus pi. Now, let me do one more thing. L0 perp is alpha prime pi plus this thing. I'll write it in terms of the A oscillators, not the alphas. The alpha minus p is square root of p, A dagger. This is square root of p, A, Therefore, we get here sum from p equals 1 to infinity, p times a p I dagger a p I. And here I get plus 1/2 sum over p, 1 to infinity, alpha p alpha minus p. That commutator is there, is equal to p, because they add up to 0, is p times nothing, well, times eta I. But eta I, or delta I, is a sum. And it's the number of transverse dimensions. So here you get, so this commutator is p delta I, or eta I, and therefore this is p times d minus 2. So we get 1/2 d minus 2 sum from 1 to infinity of p. Doesn't look very promising, does it? We're going to talk 3 more minutes and quit. I really needed to get this much done today. So what is happening here, really? It's sort of a major disaster, if you really think about it. The L0 operator, that is very crucial for us, it was the Hamiltonian. Remember, at the beginning of this lecture, we sort of said that the Hamiltonian was L0 perp. And now we find that L0 perp is a little ill-defined. And that's not good. So one thing we could say is we could say, look, who knows? Why don't we just ignore this number? Just define the operator to be this. Well, that's not all that clear. That would be a successful strategy. So we're going to try to do a little different. So first, let's see what is at stake here. We have this relation that we also have it at top blackboard. 2p plus p minus is 1 over alpha prime L0 perp. Well, we should put a question mark at this moment whether we like this equation or not. But at any rate, m squared, the mass squared, is minus p squared, is 2p plus p minus pi pi. OK, so time to decide what to do. We're going to do the following. We're not going to ignore this, but we're going to clean up our notation. So here's what we're going to do. We're going to declare L0 perp to be equal to just the first part. So alpha prime pi pi plus sum from p equals 1 to infinity p a p I dagger a p I. We'll declare this to be true. But then we will say, look, this was the real formula. And the L0 that we got was really that thing on the right, whether we like it or not. So we'll change this into 2p plus p minus equal 1 over alpha prime L0 perp plus a constant a that is going to be this constant, and we'll leave it for further study, the constant a. So this is what we got. Our honest L0 was ambiguous. It had a constant here that even came out to be infinite, and we have it here. So here I'm going to put L0 plus a in order to distinguish something that is totally well-defined, this L0 perp, plus this constant that is not well-defined. But then when we go to the mass squared formula, we obtain the following. Mass squared is 1 over alpha prime L0 perp plus a minus pi pi And L0 perp, L0 perp is here. The PI's will cancel. So at the end of the day, we get that the mass squared is a very simple formula, 1 over alpha prime, sum from p equals 1 to infinity, p, API dagger, API, plus that constant, A. So this is our formula. And that constant is ambiguous at this moment. So, punchlines. Here are the punchlines. This constant A is equal to 1/2 d minus 2 times the sum of integers from p equals 1 to infinity. And this constant, well, it's either 0 or it's infinite or some other number, and it affects the masses of all your states. So if you ever want to hope to find the mass of any quantum state of the string, you have to figure out what this constant is. And it's ambiguous. So you have to do something. What we're going to do is going to be Lorentz invariance. We're going to demand Lorentz invariance, and the constant will be fixed to a number. And you will say, well, that's the number, and that's it. That's your theory. That's the definitions. You've made the definitions. You make the rules. Now, I want to emphasize again a couple of things. These are the oscillators, and now you see, remember for a harmonic oscillator, the Hamiltonian was H omega A dagger A. Now you have A's with indices, a P and a P here, and I's, but the omega is growing with P. So these are, the higher ends are oscillators of higher and higher energy. More modes excited on the string, more energy. Now, we talked about this thing, that in the classical theory, we would have very few massless states. There was no A term. If the formula for the mass squared was this, anytime you have a state with any oscillator, it would be massive, because it would give a positive contribution. So actually, it's good that we got something here. There's hope. But it would have to be negative, because if it's negative plus a positive contribution, you can get 0 mass for some interesting states. And it doesn't look like it wants to be negative. But here, again, something either strange or remarkable happens, that you can try your best to define this number. And the best way to define it is through the zeta function. The zeta function of S is defined as the sum from P equals, n equals 1 to infinity, 1 over n to the S, where S is a complex number. And in the complex S plane, it has to be bigger than, the real part has to be bigger than 1. Real of S is greater than 1. Then it converges. This definition is the famous Riemann zeta function. Now, the famous Riemann zeta function is defined by this sum here, but it's an analytic function, so you can define it everywhere you want. And you can ask, this sum seems to be precisely zeta of minus 1, because if you take minus 1, the power, the n is up, and you have the sum of all integers. And you can ask any mathematician friend how much is zeta of minus 1, the analytic continuation, and it is minus 1/12. So in some sense, this sum is minus 1/12. This is totally crazy, but there's good reasons to believe it's right. In that case, you get minus 1/24 d minus 2. And in order to get massless states here, these things have unit energy, so you're going to need A to be an integer, and the lowest integer it could be is minus 1, and that fixes D equal 26. So things are beginning to show up here. in a very crazy way. Now, if you don't like this, we're going to use it from now on, that sum of all integers is minus 112, all these things. There is one formula that is actually quite nice, and it's this. You can try this sum. Maybe it will make you feel a little better. N equal 1 to infinity of n is divergent. But if you put e to the minus epsilon n with any epsilon positive, that is convergent, as long as epsilon is equal to 0. And then how does it diverge as epsilon goes to 0? It diverges like 1 over epsilon squared. But then you get, if you calculate it, you get minus 112 plus finite. So it's the same 112 here, that somehow is the finite part of something that is infinite, and in some sort of regularization scheme, it turns out that only the finite part matters. But we will do this without hocus pocus. This is hocus pocus, but it's so useful that everybody uses it. So from this, you can find, for example, that the sum of the odd integers is plus 124. Or you can find all kinds of sums that are totally crazy, but they give you the right answers in every situation that has been tested. And the correct way to do it is with the Lorentz algebra. So you put an A here, where we put it, and we'll go and check the Lorentz algebra, and the closure of the Lorentz algebra is going to say A is minus 1, D is equal to 26, and all will be derived logically. But the shortcut is so good that everybody uses it. Sorry for this time. We went over, but we finished at least what we needed to do. Sorry.